Imagine stepping into a hidden realm where the interaction of two immiscible liquids creates a delicate balance that can only be maintained through molecular ingenuity. In this microscopic universe of microfluidic devices, surfactants act as indispensable mediators that enable oil and water to engage in a controlled dance at their interface. Picture a grand banquet where guests, who would typically shun one another, are gently guided by an expert host to mingle in harmony. In this scenario, surfactants, with their dual affinity for both water and oil, position themselves precisely at the boundary between the two fluids. Their hydrophobic tails dissolve into the oil phase while their hydrophilic heads remain in the water, thereby reducing interfacial tension in a manner analogous to easing social tension at a crowded party. This reduction in tension is critical because it transforms a chaotic interface into a stable platform where droplets can form uniformly. One might ask, the answer is clear. Without surfactants, the natural repulsion between oil and water would lead to large, unstable droplets that would coalesce uncontrollably, rendering the microfluidic system ineffective for high-precision tasks. Delving deeper, the role of surfactants becomes even more fascinating when we consider the molecular rearrangements that occur at the interface. As these molecules assemble, they create a structured, quasi-two-dimensional film that stabilizes the boundary by lowering the free energy of the system. Imagine the interface as a high-energy barrier that, without intervention, would cause droplets to merge in an effort to minimize surface energy. The introduction of surfactants is like installing a sophisticated security system that not only reduces the energy barrier, but also actively prevents droplets from coming too close and merging. For example, in the fabrication of emulsified drug delivery systems, surfactants ensure that each droplet remains isolated, acting as a tiny, independent reservoir for active pharmaceutical ingredients. When one wonders how this process affects droplet shape and stability, the answer is that by lowering the interfacial tension, surfactants allow droplets to adopt a nearly perfect spherical shape, a configuration that naturally minimizes surface area and therefore energy. This spherical form is essential in applications like digital microfluidics, where uniform droplet size directly correlates with the consistency and reliability of biochemical reactions. The influence of surfactants extends beyond mere droplet formation. They are pivotal in managing droplet coalescence as well. In a dynamic microfluidic environment, droplets constantly interact as they travel through channels, sometimes colliding or coming into close proximity. Without the protective barrier provided by surfactants, these droplets would readily merge into larger, less controlled entities, disrupting the precision needed for processes such as single-cell analysis or high-throughput screening. Imagine a scenario in which each droplet is like a tiny vessel carrying precious cargo. Surfactants wrap around these vessels like a protective cloak, preventing them from colliding and fusing with one another. When asked if this protective mechanism is always sufficient, the answer is that while surfactants significantly reduce coalescence, their efficiency depends on factors like concentration, the nature of the fluids, and the dynamic conditions within the microchannels. For instance, under high shear forces, even well-stabilized droplets might be at risk of merging if the surfactant layer is disrupted, underscoring the need for meticulous formulation and system design. In practical terms, the selection of a surfactant is a highly nuanced process that requires careful consideration of multiple parameters. Researchers must balance the concentration of the surfactant to achieve the optimal reduction in interfacial tension without exceeding levels that might lead to the formation of micelles, aggregates that can interfere with droplet behavior. Think of it as seasoning a gourmet dish. Too little and the flavors do not blend. Too much and the dish becomes overpowering and loses its intended character. In the context of microfluidics, using an insufficient amount of surfactant could leave the interfacial tension high, resulting in droplets that are prone to instability and coalescence. Conversely, an excess may lead to the creation of micellar structures that could sequester important reactants or disrupt the overall flow dynamic. When asked what happens under these circumstances, the answer is that precise calibration of surfactant levels is essential, and advanced analytical techniques such as tensiometry and high-speed imaging are employed to monitor and adjust these concentrations in real time. Beyond the realm of concentration, the chemical structure of the surfactant plays a crucial role in dictating its performance within microfluidic systems. Different surfactants offer various advantages. Some are designed for biocompatibility, making them ideal for medical diagnostics and therapeutic applications, while others might be optimized for chemical stability or specific interfacial interactions. For example, non-ionic surfactants are often favored in biological applications due to their lower toxicity and reduced likelihood of interfering with delicate biomolecules, whereas ionic surfactants might be chosen for their stronger electrostatic interactions in systems where robust droplet stabilization is paramount. One might ask, how do these molecular differences translate to real-world performance? The answer is that the choice of surfactant can determine not only the size and uniformity of the droplets, but also their longevity and resistance to environmental fluctuations. In one instance, researchers developing a microfluidic platform for cancer cell analysis chose a combination of non-ionic and ionic surfactants to create a balanced system that maintained droplet integrity under varying temperature and flow conditions. The practical applications of surfactant-generated interfacial phenomena in microfluidics are vast and continue to expand as our understanding of these processes deepens. In the field of chemical synthesis, for example, the precise control over droplet formation afforded by surfactants allows for the creation of uniform reaction microenvironments. These controlled droplets act as microreactors, each facilitating a specific chemical transformation under nearly identical conditions, which is crucial for producing high-quality, reproducible products. A real-world example can be seen in the synthesis of nanoparticles, where uniform droplet size translates directly to uniform particle size, a key factor in ensuring consistent catalytic activity or optical properties. When asked whether these advances could lead to more efficient industrial processes, the answer is yes. By harnessing the power of surfactants to fine-tune interfacial properties, industries can achieve greater consistency and efficiency in production, ultimately reducing waste and improving product quality. Environmental applications also benefit from the precise control of interfacial phenomena via surfactants. In water treatment systems, for instance, microfluidic devices can be used to encapsulate and release reactive agents that break down pollutants. Surfactants help maintain the integrity of these encapsulated droplets, ensuring that the reactive agents are released in a controlled manner only when needed. Imagine a scenario where each droplet is a tiny capsule carrying a remedial agent that neutralizes a contaminant. Without surfactants, these capsules might burst prematurely, leading to inefficient remediation. When queried on the effectiveness of such systems, the answer is that surfactant stabilization is a cornerstone in designing responsive and adaptive environmental technologies, providing a means to address pollution with high precision and minimal collateral impact. In the realm of medical diagnostics, surfactants are equally transformative. Digital PCR, a technique that relies on the compartmentalization of reactions into thousands of tiny droplets, depends critically on the stability imparted by surfactants. Each droplet acts as an independent reaction vessel, and any coalescence between droplets can lead to cross-contamination and false reading. Here, surfactants ensure that every droplet remains isolated, maintaining the accuracy and sensitivity of the assay. Consider a diagnostic test designed to detect a rare genetic mutation. The reliability of such a test hinges on the uniformity of the droplets, which is achieved through careful surfactant selection and optimization. When one might ask whether advancements in surfactant technology could further improve diagnostic accuracy, the answer is affirmative. Ongoing research into smart surfactants, molecules that can adjust their properties in response to environmental cues, holds the promise of even more robust and adaptable diagnostic platforms. Looking to the future, the evolution of surfactant technology in microfluidics is set to revolutionize a wide array of applications. Emerging research is focused on developing responsive or smart surfactants that can alter their behavior in response to changes in temperature, pH, or other environmental factors. These adaptive surfactants would provide an additional layer of control, automatically optimizing interfacial properties in real time to maintain droplet stability under fluctuating conditions. For instance, in a microfluidic device operating under variable thermal conditions, smart surfactants could adjust their configuration to continuously maintain low interfacial tension, ensuring consistent droplet formation and preventing coalescence even in the face of external disturbances. When asked how such innovations might impact future technologies, the answer is that they could pave the way for highly adaptable and efficient systems in areas ranging from personalized medicine to advanced manufacturing, where the ability to control matter at the micro scale is paramount. Ultimately, the study of interfacial phenomena in microfluidics, with a special focus on the role of surfactants, reveals a complex yet elegant interplay of chemistry and physics that is crucial for the advancement of numerous high-tech applications. Surfactants, by modifying interfacial properties, not only facilitate the controlled formation of droplets, but also serve as a safeguard against the unpredictable merging of these droplets. Their impact is felt across diverse fields, ensuring that microreactors remain stable, that chemical syntheses yield uniform products, and that diagnostic assays produce reliable results. As we continue to explore and innovate, the integration of advanced surfactant systems, particularly those that can respond dynamically to their environment, promises to further elevate the capabilities of microfluidic technologies. In essence, the future of microfluidics will likely hinge on our ability to harness and refine these molecular mediators, transforming the way we manipulate fluids on the smallest scales and opening up new avenues for scientific and technological breakthroughs.